Good afternoon, and thank you for setting this up. Okay, I have disclosures, but they're not related to this talk. You all know that TMS is stimulating the cortex directly via electromagnetic field. But of course, the TMS, this is what I show here in yellow. But TMS also produces a sound which stimulates the ear, and it has somatosensory and motor input via muscle twitches and stimulation of the peripheral nerves. Before getting into the detail of my study, I would like to make 3 points about these peripheral components, which I think the community is largely unaware of. The first one is that actually the somatosensory stimulation often doesn't happen in the nerves which are close to the coil, but due to eddy currents, TMS is actually a really brilliant tool to stimulate the trigeminal nerve and the facial nerve at the base of the skull. So here we get a nerve stimulation or not a nerve fiber stimulation. There's a very beautiful study which I recommend you to read, which is quite old, which actually checked this. This is Smith in Muscle and Nerve 95. And they actually used a coil and put it over different parts of the, where we normally stimulating, let's see, C3, or can I use this here? Yes. Here, you see this here, C3 and P3, where we normally would also stimulate for TMS. And what they looked at was the peripheral evoked response in a trigeminal muscle or in a facial muscle. And what you can see is that you get a response which has a latency of 5 milliseconds. That means it's actually stimulated in the foramen, not in the periphery, at the normal sites where we're normally stimulating with intensities which we are normally using. So in between C3 and P3, also between T3 and OZ, actually parotile, you get a facial stimulation, but often also a trigeminal nerve stimulation. And the higher the intensity, the stronger this is. This is very relevant for our evoked responses. This is a similar work from Risto, where this is actually the first publication of a TMS evoked response, where we stimulate the motor cortex here at 3 milliseconds. But you see this effect at 24 milliseconds later here, which is actually over the phase representation of the part we have stimulated. So here the ambiguity starts. Is this really a transcallosal motor response, cortico-cortical, as claimed in the paper, or is this actually a peripheral response by stimulating the nerves? I don't think so, but it's just open. Another thing which is important is that we also have the dura mater. The dura mater is not something which is not sensory which is kind of without sensory innervation. You have actually slow conducting but also fast conducting axons, and most of these axons are actually running in parallel to the sagittal sinus, so they can actually be also stimulated by the stimulation. So even if you would use a numbing cream, the dura mater we cannot get rid of and might be stimulated. You have also Ruffini-like receptors very close to the superior sagittal sinus, so by the mechanic vibration you can activate the dura mater. So we have a nerve stimulation in the foramen, and we have also the dura mater stimulation, which has actually not systematically studied. And then we have the auditory stimulation, and this is a work by Risto, which actually shows the importance of bone conduction. So this is an auditory evoked response, and you can see if you have the coil on the head, you have an air bone effect, and you get a large response. If you put a plastic cube in between, you actually can dampen it. You have still a bone conduction, but it's dampened. But if you put it in air, you actually have only 1/3 of the response. That means 2/3 of the response is actually coming through bone conduction and not through the air. So these are 3 important things which I think are important. So if you do a sham stimulation with the coil in the air, it's not a realistic sham. It's just useless because you just reduced by 2/3 the sensory input. And now I'm talking a little bit about our paper, which has been published recently in Neuroimage. It's actually motivated by another paper by Herring in Journal of Neuroscience, where they used this control condition here by stimulating the occipital cortex, and they find this late response after sham, which mimicked very much the TMS responses. And so we were concerned in a study we did whether the peripheral response could actually contribute. And that led to this study, which we just published, which basically tried to mimic the sensory and the auditory input, and we did this by using a bipolar electric stimulator, putting the coil on top of it. Of course, you can also see here the bone conduction is not as strong, therefore we increased a little bit the intensity of the coil in order to match this. But the idea was to get a sensory auditory stimulation, which does not an effective brain stimulation, and what kind of response would that evoke? Actually, the study was also designed to figure out what is the difference of the different coil orientations. So we targeted in the same subjects 2 areas, a paramedian frontal and a paramedian parietal area, so with 2 different opposite coil directions, and then we used these kind of realistic sham condition as a control. This was actually what we wanted to publish first, but now we're actually focusing on these peripheral responses. Do you have a problem when you do this? Because the electric stimulation creates a nasty artifact. So what we did is we flipped the polarity of the electric stimulation after half of the trials, and then we fitted the exponential fit to get rid of the remaining potential. But of course, if you use a very high stimulation, this is really difficult to kind of correct for. The intensity we used here to match the peripheral input, that's very important, was roughly 10 milliamps. So you have to stimulate quite high in order to actually match the intensity of the TMS. We looked at the psychophysics of this, and we were actually not able to 100% match what TMS does, but in some things we succeeded. So the intensity was matched by default, so that was adjusted. But you can also see that the focality was much more focal with electric stimulation. You can see this here versus the 2 real stimulations, which were much less focal. You have also stronger effects on the frontal side than parietal, and this is because frontal is more intense. We had also some other effects on the loudness, which were not systematically between real and sham, but there were slight differences there too, so it was not a 100% match. We also calculated with SimNIPS the kind of current flow that's induced in the cortex, and you can see that our intensity was sufficient to use a focal stimulation in the gyrus we targeted. It was estimated 60 to 90 volt per meter. The control stimulation was roughly a third of it, and that was deemed to be not effective. The intensities we used were 53 to 75% of maximal stimulus output, and we didn't look at the resting motor threshold or active motor threshold in that cohort, but we did this later in order to figure out where are we with our intensities, and it's basically matching the resting motor threshold. So we were kind of stimulating in the range of resting motor threshold, but we didn't adjust it to the resting motor threshold. And it was a focal stimulation, and we're quite sure that the sham stimulation didn't induce a real stimulation. When we then looked at the evoked potentials, this is now for the frontal side, but then also for the parietal side, you can see that the real stimulation evokes similar but not identical responses, but the sham stimulation also in the topo plot and also in the curves is very similar. And when you then look at the global mean field power, you can also see that the temporal fluctuation of the mean field power is the same. And when you then look at the different electrodes, and this is in black here, which have a correlation, a significant correlation between the different conditions, you can see that most of the electrodes show a significant correlation. So the peripheral stimulation, which was, as we think, not effective, produced exactly, not exactly, but very closely the signal that we get with the TMS. We replicated this for the parietal side. As said, it's not identical, but it was very similar. You can see here, this is the same curves, same topo plots, same curves. You can see here some differences in the mean field power here for the realistic sham. There's a little bit more difference here, and also the correlations are not as strong. But you can see for the later responses, which are it was very, very clear and was global, but it was also there for early responses. So it's not only the late responses that show a covariation. So our conclusion of this is, if you do a realistic sham stimulation that in a way tries to match the peripheral sensory and auditory input, and you match that with the TMS, in a way it's normally done, you get a similar effect, and that was what we then published and said we would like to see a realistic sham control. Our study kind of triggered a quite fierce response of the community. It was a letter in brain stimulation, and one of the important things that were raised here was that the evoked response which we obtained in real and sham are substantially different from the evoked responses of previous studies. And these studies were it was shown, this is what we found, and this was what, for instance, Mario found, but also others. And you can see they are quite smaller. Here you have really large amplitudes. So definitely what we did doesn't really tell something about this kind of TEPs. So we wrote a rebuttal and looked actually back, okay, is this really so atypically what we did? So we went into the literature and looked what has happened in the last 3 years. So which papers have been published which had a N100, and we looked into these papers and looked into the potentials. And what we saw is that what we're producing is very much in tune of 95% what people in the field are publishing. So this is a study by Sham, and it's with 120% of resting motor threshold over the same site as we did, and it's a really nice replication. So our data one-to-one replicates what they published. And then we went through the literature. We published a table with all these different things, and I go just through it here. You can see that all these papers here, and we didn't find a single one which actually used, which looked at the N100 that basically has this small response in the beginning. So everyone has very small responses here. They never be above 5 microvolt. So there are two fractions in the field, one which uses kind of a stimulation that has a high early response, but the majority of the field actually doesn't do that. They use the resting motor threshold or other ways of tuning it, and they have a very small response. And these are the papers I'm referring to. They might be confounded by these peripheral effects. When you then look at the N100, you can see this here. It's in all these studies. So you have an N100 which is in all these studies, and it's very similar in the topography like we found. It's of course sometimes a little bit different, but our point is that these studies need to have a realistic sham control, because otherwise everything what you see could simply be a peripheral effect, and you cannot say, if you claim a cortical effect by the TMS, you can actually not do that. So I would just like to summarize. We call it the PEPs. They are real. They are not something we made up. And they contribute substantially to the late part, but also the early part of the TEP, at least for those mainstream way of doing TMS EEG. So what is important? So if you do a study that claims specificity in terms of cortical connectivity induced by your focal stimulation, then I think you have to do a PEP control experiment in order to figure out is it really transcranial cortical or is it thalamocortical. And I think also another thing which is important, that one has to start to specifically assess the PEP effects, and that starts with actually reporting in the publications the perceived TMS effects. So what do people actually still hear, despite of noise masking? And I forgot to say that we use standard noise masking and foam padding. Is there still some residual hearing? How strong is the sensory input? And just document this. But I think, and there I'm kind of very dogmatic, I think for these studies I'm referring to a routine implementation of a realistic peripheral control stimulation is actually necessary, and not only one for all, but actually for each condition you do, because your peripheral input will change from site to site. And another, of course, important challenge is to minimize the TMS evoked sensory input, so to make our TMS stimulation as a kind of less loud. That would actually help a lot. And then, of course, dosing would, there might be some ways of getting the TEPs and PEP ratio better. So Mario will tell about it. So the Milano approach might have a better TEP to PEP noise ratio, but that has to be shown. I think this is the last slide I have. I'm just a little bit afraid now what the field will do in the future to actually not do what is needed to do. I think what one proposal is cleaning. So you could actually just clean it. So you do a peripheral, and then you clean it out. This is one approach which has just been published. What you can see is each of those cleaning approaches are problematic because you use a lot of the signal. It's it's smaller, and kind of ICA and other approaches are very difficult because it's temporal-spatially not independent. Some people say, okay, just let's do one control site, and that's it. But that's the problem, because I showed you the facial and the trigeminal stimulation is different at different sites. Your noise will be different because of the bone conduction, so you need to have it actually for each site. So we would say that for each site you're stimulating, for each intensity, for each patient, for each condition, you should do a control experiment. It just doubles your time of the experiment, but maybe you do less conditions, and you have a better way of looking at this. And with that, I would just thank the PEP team that actually kicked this off, and looking forward to your questions.